The universe is expanding at a rate scientists cannot agree on, and this disagreement is threatening to break everything we know about physics. For decades, cosmologists measured cosmic expansion with increasing precision, confident they were closing in on the exact number. But instead of converging on a single value, their measurements keep diverging. The gap is widening, and what seemed like a simple measurement problem has become one of the most disturbing crises in modern science. People think this is just about scientists needing better telescopes or more precise instruments, that with enough time and funding, someone will find the error and everything will make sense again. But the reality is far more unsettling. Every major method of measuring how fast the universe is expanding produces a different answer, and these aren't small differences we can blame on statistical noise or experimental uncertainty. These are fundamental disagreements that remain even after accounting for every known source of error. The methods that should agree are telling us completely incompatible stories about the cosmos, and the more precisely scientists measure, the worse the problem becomes. The number at the center of this crisis is called the Hubble constant. It represents how fast space itself is expanding, typically measured in kilometers per second per megaparsec. Think of it as the speed limit of cosmic expansion. A megaparsec is about 3.3 million light-years, an almost incomprehensible distance that contains thousands of galaxies. The Hubble constant tells us that for every megaparsec of space between us and a distant galaxy, that galaxy appears to be receding from us at a certain speed due to the expansion of space itself. This isn't galaxies moving through space. This is space itself stretching, carrying everything with it. Here's why this number matters more than you might think. The Hubble constant determines how old the universe is, how big it will ultimately become, and what fate awaits everything in existence. Change this number even slightly, and you change the entire history and future of reality. It dictates when the first stars formed, how galaxies evolved, and whether the universe will expand forever or collapse back on itself. Every cosmological calculation depends on getting this number right. Without it, we cannot make sense of the universe's past or predict its future. So when scientists cannot agree on what this number is, they cannot agree on the fundamental nature of reality. The traditional method of measuring cosmic expansion uses what astronomers call the cosmic distance ladder. Scientists observe certain types of exploding stars called type Ia supernovae, which serve as standard candles because they always explode with roughly the same brightness. By measuring how bright these supernovae appear from Earth compared to their true brightness, astronomers can calculate their distance. Then by measuring how fast these distant objects are moving away from us through the redshift of their light, scientists can determine the rate of expansion. This method, refined over decades with instruments like the Hubble Space Telescope, consistently produces a value around 73 kilometers per second per megaparsec. Teams have checked and rechecked this measurement using multiple independent approaches. The number holds. But there's another way to measure cosmic expansion that looks not at distant supernovae, but at the universe's baby picture. The cosmic microwave background is radiation left over from when the universe was only 380,000 years old, a faint glow that fills all of space. Satellites like the Planck mission have mapped this ancient light with extraordinary precision, measuring tiny temperature fluctuations that reveal how matter was distributed in the early universe. Scientists can use these measurements along with our best theories of physics to calculate what the Hubble constant should be today. This method, based on the universe's initial conditions and our understanding of how it evolved, consistently produces a value around 67 kilometers per second per megaparsec. Two completely different approaches, two completely different answers. The gap between 67 and 73 might sound small, but in cosmology, this 6-unit difference is catastrophic. This discrepancy, known as the Hubble tension, has persisted for over a decade and only grown more pronounced as measurements became more precise. At first, scientists assumed one method had a subtle systematic error that would eventually be found and corrected. But every attempt to find such an error has failed. Both methods have been scrutinized, tested, cross-checked with independent observations, and verified by multiple research teams using different instruments and techniques. Both appear to be correct. Do you see the problem taking shape? This isn't about needing better measurements. We have excellent measurements. They just contradict each other, and the confidence in each measurement keeps increasing while the disagreement remains. Statistical analysis shows the probability that this discrepancy is due to random chance is less than 1 in a million. Something is fundamentally wrong, and scientists don't know what. The implications spiral outward in disturbing directions. If the cosmic microwave background method is correct and expansion is slower than the supernova method indicates, then the universe would be older than current estimates suggest, somewhere around 14 billion years instead of 13.8 billion. This might seem trivial, but it creates problems with the ages of the oldest stars we observe. Some of these ancient stars appear to be nearly as old as this revised universe age would allow, which raises the uncomfortable question of how stars formed so quickly after the Big Bang. the timeline becomes impossibly tight. But if the supernova method is correct and expansion is faster, different problems emerge. A faster expansion rate means the universe is younger than we thought, possibly only 12.5 billion years old. Now the oldest stars become older than the universe itself, a logical impossibility that breaks cosmology entirely. Additionally, a faster expansion requires more dark energy driving that expansion, which means our understanding of this mysterious force filling 70% of the universe would need fundamental revision. What if both measurements are actually correct? This is where things become genuinely disturbing. If both methods are accurately measuring what they're designed to measure, then the universe doesn't have a single expansion rate. This would mean the Hubble constant isn't constant at all, or that space is expanding at different rates in different regions, or that the laws of physics themselves change depending on the scale at which we observe the universe. Each of these possibilities breaks our most fundamental assumptions about how reality works. Here's the real problem scientists rarely emphasize publicly. The Hubble tension might be telling us that our entire cosmological model is wrong. The standard model of cosmology, called lambda CDM, has been remarkably successful at explaining nearly everything we observe: dark matter, dark energy, the cosmic microwave background, galaxy formation, the large-scale structure of the universe. This model works beautifully to describe all of these phenomena, except now it produces two different expansion rates depending on which observations you use. And a model that gives you different answers depending on how you ask the question isn't a working model, it's a broken one. The most unsettling possibility is that we're missing something fundamental about the universe's contents or behavior. Maybe there's an unknown form of energy or matter that affects expansion differently at different times in cosmic history. Maybe the properties of dark energy have changed over time in ways our theories don't account for. Maybe gravity itself doesn't work the way we think it does on cosmic scales. Every explanation requires adding something new to physics or revising something we thought we understood. There is no conservative solution, no minor adjustment that makes the problem disappear. Scientists have proposed dozens of potential explanations. Some suggest that the early universe expanded faster than the standard model predicts. Others propose that dark energy is more complex than a simple cosmological constant. Some invoke modifications to general relativity itself. A few even suggest that the cosmic microwave background we observe might not be as pristine as we assume, potentially contaminated by foreground effects we haven't properly accounted for. But none of these explanations have gained widespread acceptance because none of them can fully explain the Hubble tension without creating new problems elsewhere. What makes this crisis particularly frustrating is that both measurements keep getting more precise, which should resolve the disagreement but instead makes it worse. Better data isn't helping, it's confirming that the problem is real. When scientists use entirely independent methods to measure expansion, like gravitational waves from colliding neutron stars or the distribution of galaxy clusters, they often get yet another answer that doesn't match either of the two main measurements. The more ways we look at cosmic expansion, the more confused the picture becomes. And here's what keeps cosmologists awake at night. If we can't trust our measurements of the expansion rate, what else are we getting wrong? The Hubble constant is woven into nearly every calculation in cosmology. It determines distances to galaxies, the ages of cosmic structures, the density of matter and energy in the universe, and the physics of the Big Bang itself. If this foundation is shaky, everything built on top of it becomes questionable. Models of galaxy formation, dark matter distribution, the timeline of cosmic history, predictions about the universe's ultimate fate, all of it rests on assumptions that now appear to be failing. The universe has presented us with two measurements that cannot both be right, but both appear to be correct. Logic demands that either one measurement is wrong in a way we haven't detected, or our understanding of cosmic evolution contains a fundamental error, or the universe operates according to principles we haven't discovered yet. None of these options are comfortable. The first suggests our experimental methods are flawed in ways we can't identify despite decades of refinement. The second suggests our best theories of cosmology are incomplete or incorrect. The third suggests we're missing major pieces of physics entirely. Scientists can't agree on how fast the universe is expanding because the universe might be telling us that our question itself is flawed. Perhaps asking for the expansion rate assumes a simplicity that doesn't exist. Perhaps the cosmos operates according to rules that make the very concept of a single expansion rate meaningless. Or perhaps we're witnessing the breakdown of our understanding at the edges of what our theories can explain. When your most careful measurements of reality contradict each other, reality isn't being inconsistent. Your understanding is. The Hubble tension has now persisted long enough and been verified thoroughly enough that it has graduated from an interesting puzzle to a genuine crisis in cosmology. Papers are published weekly proposing new explanations, each more exotic than the last. Conferences are held specifically to address this single problem. And still, the measurements remain stubbornly incompatible. The universe is expanding, of that we're certain. but we cannot say how fast with any confidence anymore. And if we can't measure something as fundamental as the rate at which space itself is stretching, what confidence can we have in anything else we claim to know about the cosmos? The gap between what different methods tell us about cosmic expansion continues to widen, even as our measurements become more precise. This is the opposite of how science is supposed to work. Better instruments and more careful observations should make answers clearer, not more contradictory. Instead, we find ourselves in the uncomfortable position of having excellent data that refuses to make sense within our theoretical framework. Something has to give. Either the measurements will eventually reconcile through the discovery of systematic errors we currently can't identify, or our theories of cosmology will require fundamental revision. There is no middle ground where both the measurements and the theories survive unchanged. The universe doesn't care whether our equations work or our measurements agree. It simply does what it does, indifferent to human attempts to describe it. And right now, what it's doing doesn't match what we expected. The expansion we observe when we look at distant supernovae doesn't equal the expansion we calculate from the early universe's conditions. Both observations are real. Both calculations are sound, yet they contradict each other. This is how physics breaks, not with a dramatic revelation, but with a measurement that quietly refuses to make sense, no matter how many times you check your work. Thank you for watching. If you want to go deeper into cosmology's biggest mysteries, you might enjoy the next video. I'd be very grateful for your support, and I'll see you next time.